Students, to understand synchronous counters, because we have already completed asynchronous counter, now to understand synchronous counter we require exhaustive knowledge of excitation tables of flip-flops, because see, in synchronous counters flip-flops will be simultaneously clocked. That means all the flip-flops will be changing states simultaneously, that is at the same time. So unless we know the excitation table, we shall not be able to uh, put the possible inputs for a possible change in output, because change in output we know, we shall be knowing. In case of a counter, the output in what sequence it will be changing, we know that, because we know in case of mod 8 counter, say, we know that after 0 comes 1, then 2, then 3, right? But with these variation of output sequence, how the input is going to change, that is important, because upon that we need to design the input, right? Because upon that the design of the input will be dependent, right? So let us go through the excitation tables. Now we have four basic flip-flops. One is the SR flip-flop, clocked SR flip-flop. We have clocked JK flip-flop. We have D flip-flop, and also we have T flip-flop, right? Let us start with SR flip-flop. Now in SR flip-flop C, we have SR inputs and Q bar output. In case of characteristic table, we maintain only Q, because we know Q bar is just the opposite of Q, right? So this is known as the characteristic table, right? That we have already seen. Now how to draw, how to write the excitation table on the basis of characteristic table. Let us see. Take this SR flip-flop, right? Let us go through the characteristic table. With clock 0, whatever may be the values of S and R, the output is going to remain in no change state, right? Philosophically we can say that if time doesn't come, then whatever may be the inputs, we shall remain in no change state. Now if time comes, then if time comes and we are not giving any input, then also shall be in no change state, right? And then if time comes, if R is 1, the output is reset, that is 0. And if S is 1, the output is set. And if both are 1, then the output enters into the rest state. Okay, so let us write the excitation table. Excitation table, right? So in excitation table, we shall be having Qn plus 1 SR and the conclusion SR, right? Now four conditions are possible. The output, Q is the output, right? So Q is the output, right? So output changes from 0 to 0. This condition is possible. Output changing from 0 to 0, right? And then 0 to 1, and then 1 to 0, and then 1 to 1. See, if the output changes from 0 to 0, that means the output Q was 0, the output Q was 0, and it is now also 0. What does it mean? It means that maybe the flip-flop is reset, because output 0, this 0 is only possible when the flip-flop is reset. And what is the condition for reset? The condition for reset is 0, 1. So we write here 0, 1. There is another thing, that output was 0 and now it is also 0. It means that the flip-flop was maybe in no change state. And in presence of clock, no change is possible when both S and R are 0. So if both S and R are 0, it is possible. So see, with both these inputs, S0 R1 or S1 S0 R0, the the output may change from 0 to 0. So that is why S will remain 0, see, and R will enter into no change state. Right? Right? Okay. Now let us understand 0 to 1. Now 0 to 1 means it was reset and it has become set. Now it will become set only when the set condition is there, because in case of SR flip flop there is no toggle condition. 0 to 1 means toggle, but in SR flip flop there is no toggle condition, so it can only be explained by the set condition. So the flip flop has become set, so the input must have been 1 0, right? S1 R0, so the conclusion will also be S1 R0. Similar in case of 0 1, right? Reset 0 1, reset. So reset reset means 0 1, and the conclusion will also be 0 1. And what about 1 to 1? 1 to 1 is possible again with two conditions. 1 to 1 means that the output was 1 and it is still 1. It means that the flip flop was in no change state. The flip flop is in no change state, and no change is possible with 0 0. One can also say that the flip flop is set, right? It is set. After all, it is set. So set means 1 0. So what do we see here? We see here that S is don't care and R is 0, right? So this was the conclusion of the first excitation, 0 to 0. 0 don't care. If the output changes in case of SR flip flop from 0 to 1, then S1 R0, 1 to 0, then S0 R1, and 1 to 1, then S don't care R0, right? This we shall have to remember, right? We shall have to remember, because see, in case of counters, in case of synchronous counters, you will you will encounter states when the output Q changes from 0 to 0, right? Then you will be asked to write what is the condition of S and R, right? So this have to be remembered, right? So let us go to the excitation table of JK flip flop, right? Again we are writing Qn plus 1, JK, right? So it can change from 0 to 0, then 0 to 1, then 1 to 0, and then 1 to 1, right? Now in case of 0 to 0, it is no change. No change means J0 K0, right? And also we can say the output has become 0, right? So 0 1 we can also write, 0 1 we can also write. So if the output in case of JK flip flop changes from 0 to 0, the input possibilities are two. Either the input is 0 0 or the input is 0 1. So the conclusion is J0 K don't care. Okay. So similarly, 0 to 1. 0 to 1 means output becomes set, right? No question about it. And set means J1 K0. But in case of JK flip flop, we also have the toggle condition, right? Toggle condition means output changing from 0 to 1 or 1 to 0, right? So considering this toggle condition, if the output changes from 1 to 0, 0 to 1, then it can also be referred as toggle, that is 1 1, right? So we conclude that if the output changes from 0 to 1, J1 and K don't care. Let's talk about 1 0, right? So in case of 1 0, what we can say that output has become 0, right? Output has become 0. And what is the condition for that? The condition is 0 1, right? But this is also toggle, right? It was 1, it has become 0. So it can also be explained by 1 1. So both are possible, right? So considering this, we can conclude that J is don't care and K is 1. And what about 1 to 1? We know no change, either no change or output has become 1. Output has become 1, so 1 0, right? So this will mean this is don't care and this is 0, right? So this is the excitation table of JK flip flop, right? Right. So this was the excitation table of SR flip flop. This is the excitation table of JK flip flop. Now we move on to the excitation table of D flip flop, right? Let us write quickly Qn plus 1 D. In case of D, no conclusion is required. You will understand, right? Let us see the characteristic table of D closely, that whatever may be the input, the output is same, right? 0 0 1 1. So if we write 0 0 0 1 1 0 1 1, output will become 0 only when D becomes 0, right? So there is no question of considering what was the output. You see what is the output, and according to that you write 0 1 0 1, right? So this is the excitation table of T flip flop. Now let us go to the excitation table of T flip flop. See Qn plus 1 T. See 0 0 0 1 1 0 1 1. This is also very easy. See 0 to 0, two conditions are there. In case of T flip flop, we can see if T remains 0, it is no change. If T remains 1, it is toggle. In case of this table also, we have these two conditions. 0 0 means no change, 1 1 means no change. So if we want no change, then the T has to remain 0, the T input has to remain 0. And if we want toggle, then the T input should be 1, right? If you want toggle, that T input should be 1. Fine. So this is the excitation table of T flip flop. Remember this, for the design of synchronous counters, programmable counters, we require the understanding, and we need to remember these excitation tables thoroughly, right? Now let us understand the application of it, right? What is the application? We want to say convert SR flip flop to JK flip flop, right? So the end product is JK flip flop, and what will be the end? This is the flip flop conversion that we are performing. So what will be the end product? That will be to your left, JK, right? You write JK, and then you write Qn, then you write Qn plus 1, then you write SR. Fine. Okay. So now you are writing the sequence of binary numbers 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. This is the sequence of binary numbers. Fine. Now see, in case of JK flip flop, right? If J and K inputs are 0, then Q0 will be retained, right? No change state, right? Q0 will remain 0. Qn will remain 0 in Qn plus 1, right? So in this case also 0 0 1 will be retained, right? Now in this case 0 1, right, output will be followed by J, right? In this case also output will be followed by j. In this case also output will be followed by j. In this case also output will be followed by j. Now 1 1 1 1 means what? Toggle, right? So 0 will be toggled to 1, 1 will be toggled to 0, right? Now if you change the see the change in the sequence, see 0 to 0, if the output changes from 0 to 0, right? So what was the condition? The condition was if 0 to 0, then is 0, r don't care. So we write here, as the output is changing from 0 to 0, so it is is 0, r don't care. And 1 to 1 means, 1 to 1 means what? The output changing from 1 to 1 is don't care, r 0. So we write that is don't care, r 0, right? Now if it changes from 0 to 0, then again 0 don't care, right? And if it changes from 1 to 0, then 1 to 0 means it has become 0, so it is a reset condition, right? 0 to 1 means it has become 1, so it's set condition. 1 to 1 means again this, so don't care 0. 0 to 1 means it has become 1, so s1 or 0. And 1 to 0 means it has become 0, so 0 1. Now what we do? We draw the K map of S, right? We draw the K map of S, and we draw the K map of R. Draw the K map of R. So it will be what? J bar K bar, J bar K, J K, J K bar, Q bar Q, right? Not writing for this, it will be same. So let us write S. So it is 0 don't care, 0 0, I'm following this sequence, right? So 0 don't care, 0 0, then 1 don't care, and then 1 0. Fine. For R, let us write don't care 0, don't care 1, then 0 0 0 1. Now here we are getting this as pair, right? What will be the answer of the pair? The answer of the pair will be J Q bar, right? So this is for S, fine. And for R, we take this pair, right? And what is the answer? The answer is K Q, right? Now we take what? Now we take the JK flip flop, right? JK flip flop clock, right? So what we want to do? We want to convert it to, sorry, we take SR flip flop and we want to convert it to JK flip flop, fine. So what is S? S is JQ bar. So we take J and Q bar. So we take Q bar here, right, and we AND it and we put it to J, right, fine. And in case of this is KQ, so R will be KQ, fine. So this is K and we take Q and put it here, right, and this is our clock. So see, inside it's a SR flip flop, but from outside it has become what? It has become a JK flip flop. So in this way, what you can do, you can convert any flip flop to any flip flop. You can convert SR to D, you can convert D to T, we can convert JK to T, any possible combinations, right? Thank you all for today.